Welcome everybody. I am super excited to be here with you for another installment of the Quantum Software Talk series. My name is Dr. Sarah Kaiser, and I work at the Unitary Fund, which we are a nonprofit dedicated to supporting the quantum open source ecosystem. Whether that be directly quantum open source software projects or open education or community materials, we give out $4,000 micro grants to help support these efforts. If you are interested in learning more about this, you can always go check out our website, unitary.fund, and learn more both about how to apply and what we've given out grants for in the past. So today, I am super excited to welcome Goutam Tamvada, who is actually one of our micro-grantees, who works in the post-quantum crypto space. Let's bring him in. Can you say hi?
Hello, can everybody hear me?
It looks like it should be working, so yeah. Is there anything else you want to say, like kind of introduction about yourself before we get going?
Yeah, sure. I work as a researcher at the University of Waterloo, and yeah, I work in the area of applied post-quantum cryptography.
Sweet. Well, I'm gonna pass it over to you. And yeah, please feel free, everybody in the audience, to ask questions in chat at any time. I will make sure to kind of ask them. And at the end, we'll have kind of like a more general Q&A where you can ask whatever you like within reason.
You can interrupt me at any point.
Sweet. I'll take it away.
Okay, so yeah, thank you for that introduction. I'm going to talk about the post-quantum cryptographic software ecosystem. And the way this talk is going to be structured is as follows. I'll start by outlining what post-quantum cryptography is and why we might need it. I'll then describe the Open Quantum Safe project, which facilitates the use of post-quantum cryptography in software applications. And finally, in this context, I'll talk about our Unitary Fund project, VeriFrodo. And so with that said, let's get started with post-quantum cryptography. So whenever you visit a website, let's say the Unitary Fund website, your computer uses a protocol called Transport Layer Security, or TLS, to establish a secure connection. TLS ensures that a third party can neither understand what is being sent, nor modify the messages without being detected, nor impersonate one of the communicating parties. And to accomplish all of this, TLS makes use of public key cryptography, namely key exchange and digital signature algorithms, which I'll briefly describe in the next two slides. Let's start with digital signatures. Suppose we have two parties, Alice and Bob, that are separated by an internet link. A digital signature scheme works as follows. Alice generates a signing key, which he keeps private, and a verification key, which he makes public. To prove the authenticity of a message, Alice can perform a computation with her private signing key and the message and produce a signature. Alice can then send Bob the message and the signature, and using Alice's public verification key, Bob can verify the signature on the message. However, no one can produce the signature without access to the private signing key. So if the signature is valid, the message must have come from Alice. Algorithms commonly used for digital signatures include the RSA and DSA algorithms, as well as the elliptic curve DSA or ECDSA algorithms. And none of these are quantum resistant. They can be broken by a sufficiently powerful quantum computer. I'll provide a very high-level overview of key exchange algorithms. And suppose again we have two parties, Alice and Bob, separated by an internet link. Broadly speaking, in a key exchange algorithm, Alice and Bob generate some private information and exchange corresponding public information over an insecure channel. By combining this public and private information, they are able to arrive at the same value, and no one else can arrive at this value without the necessary private information. Some of the algorithms commonly used for key exchange are the RSA and Diffie-Hellman algorithms, as well as the elliptic curve Diffie-Hellman algorithms. Sadly, again, all of these can be broken by a sufficiently powerful quantum computer.
I actually had a quick question about that. Which of those, like, is there particular applications where, like, say, RSA is preferred or, like, the elliptic curve? Like, are there scenarios for each of those, or are they, like, is there some sort of ranking of which is better?
Actually, so in TLS 1.3, especially, it's I think RSA is not even it's just by default it's elliptic curve Diffie-Hellman that is preferred. They tend to be faster. Like Diffie-Hellman based on elliptic curve tends to be faster. It tends to be like less. The implementations we have like are less error prone to implement, whereas RSA there can be a lot of like traps and pitfalls. And yeah, elliptic curve Diffie-Hellman is preferred these days.
Gotcha. So RSA is kind of just like a legacy sort of thing.
Yeah.
Gotcha. Cool. Thanks.
No worries. Yeah. And yeah, so to that expanding on that, on the answer to that question earlier, like as you can see, when I connect to the Unitary website, the browser uses X25519, which is an elliptic curve Diffie-Hellman algorithm. And we can also see that for digital signatures, Unitary Fund uses RSA. So it's cool that Unitary Fund is funding all these interesting quantum technology projects, but it might also just be hastening the day when its own website, along with all the others, become insecure. So yeah, currently to break these algorithms at practical sizes require on the order of like billions of operations on thousands of logical qubits. And quantum computing might encounter a fundamental obstacle that prevents it from ever scaling to such sizes, but no such obstacles have been identified yet. And I'm sure some of the listeners might be able to expand on this better than I can. But the question that keeps a lot of people up at night is, when will a large-scale quantum computer be built? And Michele Mosca, who is the co-founder and deputy director of the Institute for Quantum Computing, estimates that there is a 20% chance of currently deployed public key cryptography being broken by 2029. A quantum manifesto produced by the European Commission in 2016 considers a universal quantum computers as one of its long-term goals and makes a tentative projection of 2035 as the year in which this could be achieved. In another survey conducted by Michele Mosca and Marco Piani in 2019, 22 expert opinions were solicited about the development timeline for quantum computers. Half the respondents said that it is about 50% likely that in 15 years, quantum computers will pose a threat to currently deployed public key cryptography. And
sorry, can I ask a question about that actually? With those timelines and the studies, are there any sort of assumptions or like kind of conditionals that go into those calculations or projections?
That's a good question. I'm not too familiar with the with how these were done and like how they arrived. I think the European Commission, I think the projection was just a very was very tentative, and I think don't think there was like a detailed methodology behind like why they arrived at the 2035 number. But as for the other two, maybe someone in the audience could answer this better than I can.
No worries. I was just kind of curious because we see very wildly different projections kind of from different areas, and I was just wondering, especially in the crypto space, maybe there was some assumption, but sorry. Go on.
Yeah, no, I mean, the timeline, the quantum threat timeline, I guess like there's some variability in in the responses of the experts. So yeah. Okay, yeah. So So basically, all sorts of adversaries are recording like vast volumes of encrypted communication in the hope that if quantum computing scales as expected, they'll be able to decrypt this communication. If it takes 10 years or 15 years to develop a powerful enough quantum computer, then the communication generated today will be secret for at most like 10 or 15 years, which might be too short a period for many institutions, such as banks and governments. Therefore, even though we don't have sufficiently powerful quantum computers yet, there's still an urgent need to transition to crypto systems that are resistant to attack by a quantum computer right away. And that's where post-quantum cryptography, which is also known as quantum-resistant cryptography, comes in. Post-quantum cryptography is cryptography that is believed to be resistant to attack by quantum computers. And I say believed because what we know at the moment is that there's no publicly available quantum or classical algorithm that efficiently breaks one of these crypto systems. And also, due to their relative novelty, there's less confidence in their security. And another important note is that no quantum operations whatsoever are used in implementing these crypto systems. It's all just classical operations. And post-quantum cryptographic algorithms have been constructed using a variety of approaches. Some are based on cryptographic hash functions, such as Sphinx Plus. Others are constructed using error-correcting codes, such as Michaelis. And a fair number of them are based on lattices, such as FrodoChem, dilithium, and Kyber. And we'll be taking up FrodoChem again later in this presentation. There are also crypto systems based on mathematical objects, such mathematical objects as multivariate quadratic equations and supersingular isogenies. So given the urgent nature of the problem, the American National Institute of Standards and Technology, or NIST, whose recommendations are often followed around the world, initiated a public competitive process in December 2016 to solicit submissions for post-quantum crypto systems with the aim of recommending one or more of them for general use. The first round of this process had 69 schemes, and after 2 years during which NIST and the public got to carefully analyze and evaluate the schemes, 26 of them were selected to proceed to the next round. And after one more year of examination and analysis, 15 were selected to proceed to the third round. A draft selection is expected to be published for public comment in 2022 or 2023, and a final selection is expected to be made in 2024. And yeah, if there are any questions about that, I can take them now, or I can move on to the next section, which is the Open Quantum Safe project.
So, I did have a question about that actually. I mean, firstly, a comment: 8 years for standard development seems actually pretty fast, which is great. But how did the selection go between the rounds? Like, was there a board or panel internally at NIST? Was it kind of publicly discussed? How did that kind of filtering happen?
Yeah, so there's a group at NIST that ultimately makes the decisions, but there's also like a public forum in which people are allowed to people can post comments and updates about the various algorithms, and I guess all the time people all the time are publishing papers about these algorithms and about what they've studied. So all of that is that sort of information is being collected, and ultimately, yeah, NIST makes the decisions. Some of the things that influence the decision making is, of course, whether there have been any attacks against the algorithms, but also the efficiency, the size of the cryptographic objects and the speed and how deployable they are, how easily they can be deployed in current software environments. So yeah, factors like that are also taken into consideration while making the decisions.
I think that dovetails nicely, or perhaps answers a question from TLAC 321, which was basically as they're selecting the final candidate, will that protocol cater to the execution cost, communication cost, and energy consumption requirements of IoT embedded devices? And if not, how can we tweak the candidate to make it to make it run on those devices better? That's a good question.
Yeah, so yeah, they're being taken into consideration, and also I think there have been some research works looking at like yeah, implementing post-quantum cryptography in like in small and like IoT devices. Yeah, there are many factors, and that is certainly one of them.
Yeah, that seems particularly poignant given that a lot of IoT sorts of devices are possibly the worst at doing crypto or, kind of uh, securing themselves more generally.
Yeah, definitely. It's a lot more. It's a more challenging environment than like let's say I guess the standard desktop, or it can be a more challenging environment. Let's put it that way.
Gotcha. Oh, and Aaron just added in chat actually the link to that one of the surveys that you showed, so we can take a look to see what their assumptions were. Thanks so much for the link.
Sounds good. Yeah. Okay, so yeah, on that note, I'll be moving on to the Open Quantum Safe project. And yeah, this sort of dovetails nicely with the question. We'd ideally want post-quantum cryptographic algorithms to be secure. We'd also want them to produce like small cryptographic objects, like small public keys, small signatures or small messages. And we'd also want them to be fast. But it seems as though there's like an iron triangle at the moment that applies to the current candidates that we have. And so we'd like all three, but it seems like we can have like at most two out of these three attributes. And so that means that deploying post-quantum cryptography to current like software environments does bring up like certain challenges, and there's work to be done to examine these challenges and like how to overcome them. And so one particular effort that is being made to facilitate this transition of software systems to post-quantum cryptography is the Open Quantum Safe, or OQS project. And as a side note, I also happen to be a part of the OQS project. And for a broad overview, so the OQS project is an open source project that aims to support the development and prototyping of quantum resistant cryptography. And the workhorse of this project is a C language library called liboqs that provides implementations of post-quantum key exchange and signature algorithms. We've integrated liboqs into forks of OpenSSL, Boring SSL, and OpenSSH, and I'll explain what these are like shortly. But these integrations basically help us integrate post-quantum cryptography into protocols like TLS and SSH. And through these integrations in OpenSSL and Boring SSL, we can also provide demonstrations of post-quantum cryptography being used in commonly used applications such as like Apache and the Nginx web servers, as well as the Chromium web browser. So liboqs itself is like I mentioned, a C library with a common API for post-quantum signature schemes and key exchange mechanisms. It has implementations for all but one of the NIST round 3 algorithms. It can build on a variety of platforms and is licensed under the permissive MIT license. And if C is not your thing, then we also have wrappers in Rust, C++, Go, .NET, Python, and Java. So there's many different ways to try this library out.
So you have no excuse not to try it.
Exactly.
Also,
Yeah,
I'm very happy to see Rust on that list.
yes, it's we want to try to cater to everybody. So yeah, through liboqs, we were able to add post-quantum key exchange and digital signatures to OpenSSL, which is basically an open source implementation of the TLS protocol. This is available through a fork that we called OQS OpenSSL. And through this OpenSSL fork, we've been able to, like I mentioned, we've been able to demonstrate the use of post-quantum cryptography in applications that rely on OpenSSL, such as curl, nginx, Apache, while making little or no modifications to these applications. And here's a screenshot showing post-quantum cryptography in action, as it were. Test.openquantumsafe.org is a server running OQS OpenSSL, which means it is enabled to make connections using post-quantum algorithms. We've also built a curl against this OQS OpenSSL, and we're using it here to make a post-quantum connection to the server and retrieve a web page. And as you can see, the connection was successfully established using dilithium as the digital signature algorithm and Kyber as the key exchange algorithm. And both of these are the lattice-based algorithms that I briefly mentioned earlier. We were also able to add post-quantum key exchange and digital signatures to Boring SSL, which is another open source implementation of the TLS protocol, and actually is a fork of OpenSSL. So yeah, we have a fork of OpenSSL that we call OQS Boring SSL. And through this fork, we were able to demonstrate the use of post-quantum cryptography in Google's Chromium web browser, which is the open source counterpart to the Chrome web browser.
That's super cool. Can I ask one random question that's kind of tangential? Why is it called Boring SSL?
So the idea is sort of that, like, I think this is, it might have come originally with Dan Bernstein, but the idea is that, cryptography should be boring. It shouldn't be exciting. It shouldn't try to be fancy or flamboyant or anything. It should just be boring. It should just work. It shouldn't sort of pose any problems. And so I think so Boring SSL sort of came from that. This is security. It shouldn't be exciting. It shouldn't there shouldn't be a lot going on. It should just sort of work, and it should just sort of be secure. So it should be boring.
That's pretty great. I feel like now we need some boring quantum computing packages.
We definitely need boring post-quantum cryptography. Yeah, it's a little bit too exciting right now. So yeah, here's a demo of Chromium Chromium again connecting to test.openquantumsafe.org, and yeah, using the same combination of dilithium and Kyber. We also maintain a fork of OpenSSH that, surprise, surprise, is called OQS OpenSSH, and we've also been able to add post-quantum key exchange and digital signature algorithms to the SSH protocol. And yeah, so that's it for the Open Quantum Safe part. If I can pause for if anybody has any questions.
Is that test server still up?
Yes, it is still up.
What is the port number? I was trying to copy that URL so I could put it in chat.
6281 is the port number.
Okay. 628. Well, let's see if this works. Test.openquantumsafe.org 6281. I'm getting a 400 bad request.
Okay.
Oh, the plain HTTP request was sent to an HTTPS port. Maybe I have to manually type in HTTPS.
Yeah, I don't think I'm not sure if we have automatic redirection to HTTPS.
Okay. Sorry, go ahead.
Fine. Yeah, you can also just, if you just load test.openquantumsafe.org, you'll get a page describing what it's about, and you'll actually get a page listing all the different signature and key exchange combinations and all the port assignments for each one. So you can also sort of write a script to scrape that, I guess, and to connect against each one of them, for whenever you have some time.
Also, thanks, Doug, for putting that in the chat in real time. Sorry, go ahead.
It's fine. No worries. Yeah, so last but not the least, I'm going to talk about our Unitary Fund project, VeriFrodo. So yeah, a little bit more detail about FrodoChem. It's a post-quantum key exchange algorithm that is based on the learning with errors problem, and it has a relatively conservative security profile in comparison to the other candidates. It's still under consideration by NIST, so it's actually an alternate candidate in the third round of the NIST standardization process, and it's also being considered for standardization by the German Federal Office for Information Security. So cryptography code has to be memory safe, functionally correct, fast, and also at the same time ensure that no information is being leaked through implementation characteristics such as the execution time on different inputs. Writing code to meet these requirements is not trivial because they're often at odds with each other. And if writing the code was hard, validating the code is even harder. Code inspection is time-consuming and requires a high level of expertise, not to mention that it is often quite error-prone. Testing can detect bugs that can occur frequently, and appropriate test cases might be written to catch common mistakes. But what if there's an error that only occurs with, let's say, a 1 over 2 to the power of 64 probability, and you might not catch this when doing random testing or fuzzing, but an attacker who's carefully studied the crypto system might be able to exactly set up the conditions so that this error can be reproduced, and this attacker might know it, but you might not, because maybe the attacker has found an angle that you haven't found yet. And static analysis can also be used to identify mistakes in the code, but you can't verify functional correctness. You can't verify that the code actually does what some specification or tells that you basically cannot verify that it behaves according to what the specification says it should do.
We got a quick question from chat asking about conservative security profiles. Can you expand more about that?
Yeah, so some of the other post-quantum, actually the ones in the round 3 that are being considered for standardization right now. So some of them are the main candidates are based on lattice problems over rings, and whereas FrodoChem is just based on generic unstructured lattices is what they're called. And so there's again, I'm not too familiar with lattice cryptanalysis and what the latest advances there are, but it seems to be the case in general that there's less confidence in the security of these sort of lattices over cyclotomic rings, or as opposed to just generic lattices. I say relatively conservative because it's not the most. There are so Michaelis is also a candidate and it is in the third round, and Michaelis is based on code-based cryptography, and it's been around since sort of the 1970s, and people have looked at that and studied that for a lot longer than they've looked at structured or unstructured lattices. And there's also another scheme called Psych that is based on supersingular isogenes. But the thing there is that there's a lot of mathematical machinery over there. It involves algebraic geometry and whatnot, and it's not something that people understand too well in general. It's not something that I understand too well in general, I guess. So yeah.
I also don't get it very much at all either. So I wouldn't feel bad about that.
Yeah, someday I'll take the time to actually learn algebraic geometry someday. But yeah, so moving on to Jasmin. Jasmin is basically an assembly-like programming language that's sort of intended to fill this gap, gap in verification tools. The assembly-like syntax gives the programmer fine-grained control over the code and its output. Jasmin also comes with a memory safety checker, as well as a formally verified compiler that predictably transforms Jasmin programs into assembly programs for a specific CPU architecture. And currently only 64-bit x86-64 is supported. The assembly programs, the assembly code, that is produced by the Jasmin compiler can be incorporated into C code. And here's a brief example of that. This is a function that's actually part of the FrodoChem implementation. Don't worry about what it does or what's going on over there. All that you have to know is it's a function called jazz sample n by n bar. That's some Jasmin code that does something. And here's this code being called in the in a C program that actually is just testing this code and just doing some basic sanity checking. So yeah, okay. Then moving on to EasyCrypt. So a proof assistant is a software tool that assists users with the development of formal proofs. In other words, they're sort of programs that help you check if your proofs, or programs for that matter, are correct. And EasyCrypt is a proof assistant used for cryptographic proofs. It supports reasoning about the properties of imperative programs, such as you can reason about the correctness and equivalence of imperative programs. And what makes this really what makes it interesting is that Jasmin code can be, the Jasmin compiler can automatically convert Jasmin code into equivalent EasyCrypt code. And so you can have this EasyCrypt code can be reasoned about within the proof assistant. And whatever guarantees you establish about the EasyCrypt code will also hold for the Jasmin code. And those guarantees will also be transferred into the assembly output that is produced by the Jasmin compiler. And here, so let's work through a small example of that. Here's a function in Jasmin that takes two input arrays of 16-bit, unsigned integers, and then adds the arrays element by element and performs a modular reduction, and then outputs the resulting array. And this is sort of what the Jasmin code looks like. Relatively simple, it's not too bad. This is the equivalent EasyCrypt code that is automatically produced by the Jasmin compiler. And here's a theorem in EasyCrypt stating a correctness specification for the EasyCrypt code. And what it is essentially saying is that for all input arrays A and B, each element of the output array is the sum mod to the power 15 of the corresponding pair of elements of the input array. And so if you have two input arrays A and B, then all this is saying is that the output array, which has 64 elements, each element of the output array is just a sum of the corresponding elements of A and B, followed by a modular reduction. And if we're able to prove that this is correct, then we're able to establish some sort of a guarantee about the add function in EasyCrypt. And if we're able to establish that guarantee, we can also have that same guarantee for the add function in Jasmin. And that guarantee sort of transfers over to the assembly code produced by the Jasmin compiler.
That is super cool. I had a quick question about how Jasmin is doing all of this kind of cross compilation. Does Jasmin go to some sort of intermediate representation and then have something that can take that IL to EasyCrypt or to the C libraries?
That's a good question. I'm not too sure how it works underneath the hood. It's written in Coq, and I think there's a sort of I think there's a sort of intermediate representation that can that then goes to. Actually, I'm not sure what the differences are between transferring it to EasyCrypt and transferring it to assembly. I'd have to look into that.
No worries. I was just kind of curious because that's really cool that then. So if I understand correctly, you write your algorithm in Jasmin. Jasmin has the ability to kind of compile and give you a library you can link against in C, but It can also compile to EasyCrypt, so basically translates itself to EasyCrypt, and then you can, in EasyCrypt, do these proofs of correctness of...
Yep.
That is so cool. And those guarantees then kind of propagate backwards. to
Yeah.
say the C libraries.
They don't like propagate unconditionally. Like there's some other conditions that you have to like satisfy. So you also have to sort of verify that the program terminates and that the program is memory safe and stuff like that. But that can also, so Jasmin comes with a memory safety checker, but you can also do those sorts of proofs in EasyCrypt. So you have to do like a little bit more work to sort of make sure that they propagate all the way through, like handle these like sort of edge cases and stuff like that. But yeah, broadly speaking, yeah, you can do that. What makes it even cooler is that like you can sort of you can take these programs and then you can like sort of prove that they're equivalent to like more abstract representations, more abstract specifications, and then you can say something about the security of those more abstract specifications. You can also do like security proofs and like probabilistic reasoning in EasyCrypt.
That's super cool. Thanks.
Yeah, no worries. Yeah. Yeah, so if anyone was curious, this is what the proof looks like for the theorem I just, for the lemma, I should say, that I just showed you. It looks impenetrable, but it's not as bad as it seems. So EasyCrypt, so you can actually, EasyCrypt comes with like an integration into the Emacs text editor that lets you step through each command and lets you see what the current goal to prove is and what the current hypotheses are and how the proof state is being transformed as you go from like one command to the next. So over here, like every command is sort of delimited by like a period, and you can start with like what the you can see like you can get a sense of like at each step what EasyCrypt thinks about the proof, or like what hypothesis it has, what it thinks the current goal should be, what the program is like. So this basically is incomprehensible if you try to just like read it like that, but it's not that bad. You can actually like step through the proof like using in Emacs, and like that makes it a lot more tractable. So yeah, so I've shown some specific examples, and I want to sort of step back and take a look at the process as a whole. And if there's one slide to take away from this entire section, it's basically this slide. So, in going about this process, you start with like an algorithm specification, which could be in pseudocode. And then we take this algorithm specification and, by hand, like we try to like write out an implementation in Jasmin. Also in parallel, we try to like produce like a specification in EasyCrypt. And that doesn't have to be necessarily like EasyCrypt line by line EasyCrypt code. It could just mean like correctness conditions for like, or how sort of like lemmas or theorems for like how the implementation should behave. And what we want to do is like in trying to establish functional correctness is that we want to try and bridge this gap between the Jasmin implementation and the EasyCrypt, and the more concrete Jasmin implementation and sort of the more abstract EasyCrypt specification. And the way we do that is we can have like a Jasmin compiler automatically generate an EasyCrypt code from the Jasmin code. And then what we try to do is, we take these lemmas and these proofs, and then we try to prove them on the EasyCrypt implementation. Yeah, so we can establish these lemmas on the EasyCrypt implementation, and we can bring it in line with the EasyCrypt specification and sort of establish functional correctness. And once we have that guarantee, we can also get the Jasmin compiler to produce assembly code from the Jasmin source, which will have like these functional correctness and memory safety guarantees that we just established. And then this assembly code can be called by C code and can be used by other programs, and yeah, and can just be used in general. This was like sort of a summary of like of what I've been saying in the previous slides. So yeah, if you sort of missed the slide before or something, all you need to sort of take away is like this image basically. And yeah, so let me just like briefly describe like VeriFrodo. FrodoChem is like, it has like three parts: key generation, key encapsulation, and key decapsulation. I'll just like sort of consider them as like abstract operations for now. I can explain them if anybody would like me to, but the algorithm is like relatively simple to implement. It just involves matrix multiplication and like over like 16-bit numbers. And so the VeriFrodo project, or what we, the work that that was like funded by the Unitary Fund. As part of that, we've implemented all three parts. We've implemented Frodo key generation, key encapsulation, and key decapsulation in FrodoChem in Jasmin, and we're currently proving the functional correctness of key generation. And this sort of like, this also in comparison to the other like candidates that are like in round 3 of the NIST standardization process, FrodoChem is relatively simple to implement. It's mainly just matrix multiplication and like some modular reduction. And so this also lets us like focus more of the efforts on the actual verification part as opposed to trying to figure out how to do things in Jasmin or EasyCrypt. So yeah, some like last thoughts on this combination. The integration of Jasmin with EasyCrypt means that even highly optimized programs can be formally reasoned about. You can, it's an assembly-like language, so you have like precise control over like what the output is going to be like, and so you can like you can optimize it to your heart's content, and you can still do the extraction through EasyCrypt and try to prove stuff about even like highly optimized programs. It might be harder depending on like what the program structure is like to make the proof go through, but the proof can go through. Jasmin is definitely not production ready yet. It only supports x86-64 assembly. It does not support. There's no support for like input-output functionality for a variety of reasons. Like adding that is not a trivial matter at all. Jasmin can also be a bit like challenging to install and use. EasyCrypt also has occasional soundness issues, and what I mean by soundness issues is the fact that there are like every now and then like certain issues pop up in EasyCrypt that allow you to prove false statements, and like once you can prove a false statement, then by like there's the logical principle of explosion, which means you can prove anything you want. So you have to be like, you really have to watch out for like for issues like that. And EasyCrypt, I think there was one that was like that occurred recently because of modules, of the way like importing modules worked in EasyCrypt. But I think none of these are showstoppers, and I think what just needs to happen is more people have to use it, and more people have to try to contribute back to the projects. And these issues will get like ironed out eventually with like more users and more contributors. And yeah, so as for next steps for us, we hope to prove the functional correctness of the entire FrodoChem Jasmin implementation. So not just key generation, but also key encapsulation and decapsulation in EasyCrypt. And we also wanted to tackle the security aspect, like actually what I mentioned earlier, like making it more abstract, and then like being able to like prove some security properties and like do some probabilistic reasoning. Our current implementation prioritizes readability and correctness over speed. And also, because this was my first time using Jasmin and EasyCrypt, but we also want to develop a highly optimized version for which we can establish the same correctness guarantees in EasyCrypt. And the code is available at github.com /xbztf VeriFrodo under an MIT license. It's a work in progress, but yeah, it's certainly available. And if contributions or issues or pull requests are always welcome. I invite people to try it out and report issues or contribute back to the project. Everyone is welcome to do so. And yeah, that's it for the talk. Thank you for listening. If there are more questions, I'm happy to answer them.
So maybe just building on the last thing, is there any like suggestions you have do you have things tagged as good first issues, or kind of like what kind of skills do you think like contributors might need to have to kind of jump in and help out on that?
Yeah, that's a good question. I haven't like thought about good first issues yet. What I plan to do in the next few days is really like step up the documentation, add some CI, and also that it'd be a good idea to add maybe some first issues to the project. As for skills that people would need, I think there's some work to be done on the Jasmin side in cleaning up the code and optimizing it, making it more optimal. So there's like some implementation work to be done there. On the EasyCrypt side, I think it might be there's a little bit more of a learning curve there, but if like people have some knowledge about like Hoare logic and program verification, then there's also they can also certainly that might make it easier for them to contribute to the EasyCrypt work. But there, I can also provide resources to these to learn more about these tools. There have been courses taught. There's a course taught on EasyCrypt, for example, and there's some like guides and tutorials for Jasmin. I can certainly provide those links.
Yeah, I think, at least for myself, I kind of always expect to learn a little bit when when I help out with a new project, but it seems like, kind of from what you said, like having some sort of C or maybe lower level programming language experience might be helpful.
Yeah, that would be helpful. Yeah.
But given what you also just said about like CI and docs, contributions along those lines are always like, those count as contributions. Even if you're not directly writing code, those are really, really important for open source projects. So if you're good at CI/CD, or honestly, like when I first approach a new project, my first thing is to read through the docs, and even if it's just typos, it's a very helpful thing to do for both for the maintainers and for you if you're trying to get on board or onboard yourself to the project.
Agreed. Definitely agreed. Yeah. I can post the links. I can post them in the project Discord channel. Yeah.
Sweet. We have another question in chat, which seems fairly detailed, so maybe this is a good one to take offline. But it says, for improving the post-quantum algorithm performance, say for liboqs on an AMD 64 or PQM4 on a Cortex M4, M33, M23, are there any ideas to use the underlying hardware crypto accelerators like the TPM 2.0/ARM T? I don't know if you pronounce that T or TEE. Or are the existing TPM modules not useful and we only need an FPGA implementation?
That's a good question. I think so. I didn't mention this in the talk, but Jasmin also has support for like x86-64 intrinsics, like the CPU instructions. So I think there's support for like AVX2, and I know this is not like ARM, but like I can just like start there. There's support for like AVX2 instructions, and I believe also like AES instructions. There's some work being done to port Jasmin to ARM right now, but it's a significant effort. But yeah, my understanding is that if that work were to be done, there would also be support for like ARM specific like instructions, and that could be that is like one way to speed up the implementations. And actually, in fact, when I mentioned our next steps, like one thing we want to do for like an optimized version is we want to try to use AVX2 instructions, and there are also schematics for AVX2 instructions in EasyCrypt, so you can like use AVX2 instructions and then also reason about them in EasyCrypt. And that's something that we have planned.
Yeah, so to summarize, basically the question is, can you leverage like hardware-specific accelerations for these algorithms? And your response is yes, and some of them are in progress, depending on the actual architecture.
Yeah.
Okay. there was a lot of like three-letter acronym sorts of things, and I was just trying to summarize that up. We've gotten one more question here. Are there any open problems or research statements for implementing post-quantum on embedded systems or FPGAs? So like, yeah, basically, are there any like big unsolved problems or blockers that are kind of coming up?
So I'm not too familiar with like the embedded and the FPGA space, but I guess would the question sort of be like, is there, if I wanted to implement something in like VHDL or Verilog, like are there any like blockers to that? Or like, yeah, well, that's just, I guess, one way of phrasing the question. But yeah, as far as I'm aware, I don't think so. I don't think there are any, I think there are implementations for what I can think, I can think of off the top of my head is that some of the post-quantum schemes, the way they've been implemented, uh, use a lot of stack space, but I don't think that's an unsolved problem or that's like a major barrier. I think it can be rewritten in ways to avoid that. But yeah, I'm not too. I don't think there's any major blockers in like being able to implement these on like FPGAs or besides of course like they might be slow or they might be cumbersome to use, but fundamentally I don't think there's an obstacle.
Cool. Yeah, Stiblia added some more clarifications here about which of the architectures have kind of some progress on this. I'll say to chat, if you have any other questions, please feel free to drop them in here. I have one or two for you that are kind of more general, which is what sort of skills do you use on a day-to-day basis, like when you're working on these projects? Like, obviously things like specific to those tools, but like, are there kind of general skills or things that you could like, if you could go back in time and say, past self, you really need to learn this, it'll be helpful. What would those be?
Yeah, that's a good question. I would maybe like one thing that instantly jumps to mind is it's not like anything technical or anything. It's not a technical skill, but maybe sort of like when to give up exploring like a certain avenue and when to try to like switch the problem to a slightly different one and then like sort of attack that problem. Yeah, this is sort of something I've experienced dealing with EasyCrypt. It wasn't the easiest to like get started with, even though it's called EasyCrypt, I guess. Um, but like there were times where like I would spend a lot of time trying to like, sort of skin the problem one way. Whereas like if I just like took a slightly different perspective and sort of like just stepped back from it all and took like a different perspective, then I was able to like make a lot more progress. Um, I think I don't know how like maybe that's something I've been getting. I'm not saying I'm proficient at that, but something I've been learning more and more as I through practice. So yeah, I think that's maybe one thing. I guess knowing sometimes sometimes it might be okay to just like give up on an approach like earlier and then like try like a different approach or try to like reformulate the problem or like try to like break it down into sub problems. I think sort of like that is, yeah, I think that's a skill that I've learned a little bit by using EasyCrypt and also I guess just doing research in general.
Yeah, I think that's uh, at least also from my experience, it's pretty easy when you're like working on academic research and stuff to get really tunnel visioned and just be like, this is the problem I have to solve. I will solve it. Possibly to the point of like, yeah, just kind of losing sight of the whole problem and being able to say, okay, maybe that's not actually solvable, or maybe the tool really can't do that and I should try something else.
Yes, definitely agreed.
And one more question, which is, how did you actually get into post quantum or crypto stuff more generally in the first place?
Um, I think it was a series of like lucky accidents, I guess. Uh, I was working for a professor at the University of Waterloo, Sergei Gorbanov, and one of his students uh, happened to work at this company called Icera that that does work in post-quantum cryptography. And so he recommended me to that company, and I did an internship there. And that's how I sort of got introduced to post-quantum cryptography. And then I also took a course with Douglas Sevilla, my current boss, about the like lattice-based cryptography. And then it just so happened that like around that time, a job opened up on the Open Quantum Safe project, and I started working. One thing led to another, and I ended up working for the Open Quantum Safe project. So that's sort of how I got into it.
Were you studying crypto, like just general crypto already in undergrad, or like kind of what got you interested more generally in like cryptography?
I think I had like an interest, even though and specifically like my program was like very structured, and like there wasn't much leeway for us until like the fourth year. So it's not like I had, sometimes like I didn't quite have a choice, but I just like took whatever courses we had to take. But I always had like a general interest, I guess, in like in privacy and in like Tor, in tools like Tor and like Signal and all of that. So I think that's sort of how I got into the whole thing in general. And yeah, I just happened to come across a posting by Professor Gorbanov on when I was applying, and like I just decided to apply to it on a lark, and that's how I got into this stuff.
That's pretty cool. Yeah, also pro tip, everybody, you should use Signal for messaging. It's end
Yeah,
to end encrypted because it's not just your own security, it's who you're talking to as well.
I I 100% endorse this message. Yes.
Yeah, so the little bit I know about this is basically because I did not post quantum crypto, but I did quantum key distribution and quantum crypto hardware. So kind of the other approach to the problem of using the quantum hardware that we think is going to compromise the security protocols we know now, and use it to like make hardware systems that can also do crypto. But it's far less practical than what you're talking about. You can actually run it on hardware and usefully deploy it. But
It's, I guess, more secure but less practical. I mean, post-quantum cryptography could still be, because somebody could just come up with a quantum algorithm in like 5 or 10 years, and then we'd all have to scramble to rush to the next set of algorithms. But I guess with QKD, hopefully that's not the case.
yeah. Um, is there like, so along those lines, maybe one other quick question, like for the NIST process and stuff, it sounds like the goal is to select a final candidate. Is there kind of like thoughts around like having a backup that's a different sort of protocol that could allow that pivot to happen a lot more quickly than another 6 or 8 years for standardization?
Yeah, no, so I don't, I would say actually the intention is more, especially like considering all the trade-offs that the candidates are presenting. I think the idea is to maybe select like a couple of them and sort of recommend them for use in like different situations. Um, like I mentioned, for example, Michaelis, based on code-based cryptography, we have like more confidence in its security than like some of the other candidates. And Sphinx, which is based on like hash functions, hash functions have been around forever and they've been studied for like a long time. We have more confidence in the security of those things. So uh, what I sort of see is, and maybe Douglas has more insight into this, but what I sort of see is for high security situations, or like in situations where security is paramount and not necessarily speed or sizes, then the recommendation might be to use Michaelis or to use Sphinx. Whereas in less critical situations, it might be to use like one of the other post-quantum algorithms. So I think it's sort of going to, recommendations might be along those lines.
Gotcha, that makes sense. One okay, chat that generated one more question in chat, and then we'll call it. But they asked, will QKD be more secure than post quantum?
Uh, that's a good question. I mean, if somebody proves that one-way functions exist, that I guess there shouldn't be. I mean, the thing I guess we have in cryptography right now is that we have like a bunch of things that we think are secure, but we don't actually have a proof that they're secure, that like they're that they're secure. Like for example, when I mentioned post-quantum cryptography, there's always nobody has proved that there isn't an efficient quantum algorithm to attack these candidates, and so that's sort of like always hanging. It's like a dark cloud like hanging over our heads. QKD doesn't have that. Well, I'm not too familiar with QKD. I guess like authentication is still done classically.
Yeah,
But
like you should really. So the only like quantum crypto protocol that we really have worked out in detail is key exchange. So like none of the other standard crypto protocols. But one of the biggest issues, like in principle, it's provably secure, which is way better than computationally secure, which I think is generally how even the post quantum crypto stuff is, right?
yeah,
Yeah, so in principle, it would be better. The problem is that, it's very hard to implement a device, in the same way that we can't prove, at least at the moment, that there won't be a quantum algorithm. We also can't prove that at the moment, really, that these hardware devices match the models that you need to ensure that provable security. And so, like, I actually worked on finding side channels into the QKD hardware. It's surprisingly easy at the moment, but that's fair because it's still in a pretty early prototype-y sort of stage. Um, and Aaron says, and QKD will depend on who runs the hardware. Exactly. Yeah, so I think they're like, a lot of times people trying to pit those, both QKD and post quantum crypto against each other. But I kind of feel like, and I'd be interested in your thoughts but I think they're kind of like complementary in that they solve different problems or like address different problem regimes.
yeah. Also, sort of picking up on like what you mentioned, like it's in principle provably secure. So I guess if an intelligence agency wanted to talk to itself, if they wanted to, I mean, for certain like applications like that where like you have like a lot of like state power and like you can sort of ensure a bunch of things like go according to plan. I guess I could sort of see QKD being used in situations like that. But yeah, I would say definitely at the moment, like post quantum cryptography is more practical. It's like anybody can like deploy it anywhere, and it's probably what's going to be in like TLS for a while.
Yeah.
Yeah, but
Yeah, QKD is
yeah,
definitely you are a state actor sort of threshold at the moment, just because key generation rates are so low.
yes.
Yeah.
Yeah, you also mentioned like side channel like devices, and you have to trust and you sort of have to trust the operators. So like those sorts of things, I guess you really can't like you can't trust like another person on the internet to do all of that. But yeah, if it's a government, you can sort of I guess enforce those things.
What? I can't trust people on the internet?
Yeah, I was also very shocked, surprised when I.
All right. I think I feel like we could talk about this for a long time, but I think I'm going to call it here. But thank you so much for joining us, Goutam, and sharing, kind of all the VeriFrodo project that you're working on. I'm actually super excited to take a look at it because I think being able to like prove or like formal verification as a task seems like a really cool thing to be like applying and using in the crypto space.
Agreed. I think we need more and more of it. It seems like people are moving in that direction where like they're trying to formally verify more and more stuff.
Because humans are not the best at writing code, or at least writing bug free code.
Definitely.
Cool. Well, thank you so much, everybody, for joining us today on Twitch. And if you're watching it later, thank you for watching. I hope you have a great day. You have a great day, Goutam. And certainly, if you are interested in this project, take a look at the VeriFrodo project. You can find links either in chat or on the Unitary Fund page at unitary.fund/talks. You'll find everything you need to know about this project. So, yeah. Thanks again.
And hope you have a nice day as well.
Yeah. All right. Cheers, everybody.